This is our third lecture series. It's part of the SRR second annual internship lecture series. Today, our speaker is going to be Mr. Bill Dornsife. I've known Bill for years. Bill's going to be talking about the 3 Mile accident at reactor number 2. He was actually present during the response. Bill graduated from the U.S. Naval Academy in 1966 and served several years on a nuclear submarine after completing nuclear power school and prototype. After his naval service, he served as an MS degree in nuclear. He got his nuclear engineering degree from Ohio State. Then he worked for about 3 years in a major engineering company, designing nuclear power plants and performing licensing functions before joining the Commonwealth of Pennsylvania's Bureau of Radiation Protection in 1977. While in that service, Mr. Dornsife was the state's first nuclear engineer and was a key participant in the response to the TMI accident. As director of the Division of Nuclear Safety, he was instrumental in developing Pennsylvania's low-level radioactive waste program, which included siting criteria and involving stakeholder involvement throughout the process. In 1993, Mr. Dornsife was promoted to the director of the Bureau, and in 1998, Bill retired from state government service after 22 years of service. He then joined Waste Control Specialists as a vice president of nuclear affairs and the corporate radiation safety officer. Bill was promoted to executive vice president for licensing and was responsible for the successful licensing of the byproduct disposal facility and the nation's first low-level waste disposal facility under the NRC's Tennessee CFR Part 61 criteria. He retired from WCS in 2015 and currently does consulting work. He's a registered professional engineer in the Commonwealth of Pennsylvania. He is the state's first regulatory person to be elected as a member of the National Council on Radiation Protection and Measurements, primarily in recognition of his radioactive waste management experiences. With that, Bill, I'm going to turn this over to you to begin your presentation. And again, thanks so much. And at the end of your presentation, we'll hold questions and answers.
Okay, I think I got it now. Everybody hear me?
We can, thank you.
All right. Thank you, Scott. Yeah, you and I have worked together for quite a while. Well, this is an aerial view of the 3 Mile Island plant, which is currently closed. In fact, Unit 1, which is in the background here, it's also closed because of a power cost issue. It was closed, I guess, about a year ago, and is remaining closed. The TMI-2 plant is in the foreground, and this is the reactor building for Unit 2. Just to give you a little preamble for me, as Scott mentioned, when I graduated with my master's from Ohio State, I went to work for an architect engineering company, Burns and Rowe, and I began working on the Forked River plant, which was eventually canceled, and I was transferred over to the TMI-2 plant, where Burns and Rowe had designed primarily some of the secondary systems. In 1977, I saw that Pennsylvania was looking for their first nuclear engineer, because we had like 10 nuclear power plants in the Commonwealth, and the state was becoming concerned about NRC's regulation of these power plants. So we wanted someone that could basically visit the plants and kind of provide oversight. So I applied for the job, and it took a while for the state to approve the job. So in the meantime, there was an opening at the TMI-2 plant for a design construction liaison job. Well, I took that job, and me and my family moved to the Harrisburg area. And during that time that I was the design construction liaison, one of my jobs was to actually develop criteria and implement the new NRC requirements for jet impingement and pipe whip. This required me to be extremely familiar with all of the safety systems at the plant, and I literally had to walk through the entire plant to determine whether there was any issues with jet impingement or pipe whip. So I was very familiar with the TMI-2 plant when I took the job as Pennsylvania's nuclear engineer. In fact, some of the NRC folks were extremely surprised for a quote state person how much I knew about the plant. What I'm going to cover is the cause of the accident, the accident response from the state perspective, and personal stories from my involvement. I could talk for hours. It's amazing how, things that were traumatic in your life, you remember exquisite details of that experience. And I swear that when I don't know the names of my wife and children, I'll still remember what happened at TMI. And then finally, I'll go through some lessons learned. This is the control room of the TMI-2 plant. As you can see, there was numerous indications and controls. And, one of the main lessons learned is that this plant was not very operator friendly. It was behind the times based on the state of the art for control panels. For example, chemical plants had a much more refined control panel. And it's said that during the course of the accident early on, 200 alarms went off. So you can imagine how confusing this was to the operators. This is a schematic of the TMI, of primarily the TMI-2 systems that were involved in the accident. The incident started at 4 a.m. on Wednesday, March 28th, 1979. And what initially happened, there was a malfunction in the condensate polishing system, which caused, before I do this, the plant was at the time operating at 100% power. It was still undergoing testing. It had not entered commercial operation. The condensate polisher system tripped, causing a trip of the condensate pump, and then a trip of the feed water, which obviously then caused a turbine trip, which resulted in a reactor trip. Well, immediately, without the cooling effect, the temperature and pressure in the primary system immediately started rising, and this caused the pressurizer level to start increasing. In turn, this plant was designed with a power-operated relief valve. and this power operated relief valve opened, which it was supposed to do. Unfortunately, when the pressure surge stopped, the valve did not reclose. But the indication that the operators could see was the power to the valve. It wasn't the actual position of the valve, and that led them to believe that the valve had reclosed. Now, this same incident happened at another Babcock and Wilcox plant in Ohio. However, at the time, there really wasn't a very good system for comparing these incidents, and the TMI-2 operators were not aware of this previous incident. At the Ohio plant, the operators were able to determine early on that this had occurred, and they closed the block valve, so nothing happened. Because the block valve remained open, the pressurizer continued to rise. The operators, all being Navy trained, and one of the commandments of the nuclear Navy was to never let the pressurizer go solid, because if it does, you obviously lose all pressure control, and you could cause a rupture of the primary coolant system. So the operators, seeing this, began throttling back the makeup pumps, which had started automatically on the reactor trip, and the other parameters that were changing. If they would have left their fingers off that makeup pump, nothing would have happened. The plant would have continued to be, the core would have continued to be covered. No voids would have occurred in the primary system, and everything would have been fine. In addition, they eventually actually turned off these pumps because of the concern about the pressurizer going solid. While this pressurizer power operated relief valve was open, it was spilling water into the reactor coolant drain tank. And the drain tank eventually overflowed, and reactor coolant accumulated in the sump of the reactor building, and it was pumped over to the auxiliary building into the liquid rad waste tanks. Now, obviously, and this was a lesson to learn, the reactor building should have isolated, but it didn't. It only isolated on a 4 psi pressure signal, and that didn't occur until much later. So this was pumping continuously, and eventually these tanks overflowed, and there was about a foot of water on the floor of the auxiliary building. Also, early on, the auxiliary feed water system or emergency feed water system started again automatically. However, in violation of tech specs, the block valve was closed. That was obviously not supposed to be like that. It took the operators several minutes to realize that no water was getting into the steam generators, and the steam generators boiled dry. This later, and then finally they opened the valve, and cold water was injected into the steam generators, which started obviously removing heat. This later led, cold water impinging on those tubes led the operators to believe that there could be primary to secondary leaks in the steam generator, and in fact, they isolated the B steam generator. So the A steam generator was the only one available to remove decay heat. Eventually, because of the loss of water in the system, the reactor coolant pumps tripped, so there was no flow in the system. And obviously, as the level kept decreasing, the core became uncovered. Now, the operators were not aware that this was happening because there was no indication of core level, and they also had no direct indication of the temperatures in the core. The only thing they had was a panel where they could go in and take voltage readings, and that wasn't done in the early stages when this was occurring. So the operators, were really without a lot of necessary information. Eventually, because of the temperatures in the reactor coolant drain tank and also, some other indications, they realized that this valve was probably not closed, and they shut the block valve. Also, obviously, the releases that occurred were entirely noble gases, primarily xenon and iodine, which, as you may be aware, is primarily the primary radionuclides that are in the gap activity of the rods. So when the rods have either holes or become destroyed, they release this xenon and iodine. And obviously, if reactor coolant, all radionuclides could be released when the core is melting. The other thing that happens when steam impinges on the fuel rods, it generates hydrogen gas. And we all know that hydrogen gas is flammable and could be, in fact, explosive. And this is an important thing to remember for later on in the scenario. Also important to notice is the makeup system. There's a makeup tank which provides a head for the makeup pump to continue pumping. Obviously, during the course of this, all of the noble gases were accumulating in this makeup tank. And obviously, if the makeup tank becomes empty with gases, it could affect the operation of the makeup pump. So there's another system where they can compress these gases into the waste gas decay tank. Now, I think it's also important to notice that the makeup tank relieves or can be vented to the auxiliary building, and that release goes through a filter system that primarily removes iodine, but the relief valve on the waste gas decay tank is released downstream of that filter. So obviously, if the waste gas decay tank was relieving, it could drastically affect releases. So that becomes also an important factor later on in the accident. Let's see, anything else that's there's other systems. When the pressure goes down, there's a core flood tank that automatically injects, and then there's a a long-term decay heat removal system. I think that's it. Well, also eventually, when they reestablished condenser vacuum, they dumped steam through the steam dump to provide uh, cooling for the reactor. Early on, the primary method of cooling was feed and bleed. They would feed makeup water into the system, and there's a heat exchanger in this makeup system where they could remove some of the decay heat. Obviously, it wasn't the most effective way to remove decay heat. Now I'm going to talk a little bit about accident response from a state perspective, and primarily, my experience during the 2 weeks after the accident. What the plant declared an emergency, first a site emergency and then a general emergency at about 7:25 that morning. Obviously, about almost 3.5 hours after the incident occurred. It was declared because there was high radiation levels in the reactor building. Our procedures called for, and we had emergency procedures. Our bureau had emergency procedures, and we were responsible for getting information from the plant and also making protective action recommendations, which I think is important to remember for what happened later. The first call from the plant was to the Pennsylvania Emergency Management Agency, and they in turn were needed to call somebody from our bureau, which was me, to call into the plant control room. Well, I got that call about 7:30 in the morning. I was getting ready to go to work, and I called into the plant, and obviously it sounded very confused in the background, and I started asking questions to the person I was talking to, and it became clear to me that they really didn't quite have a handle on what was really going on. Then I heard in the background, now evacuate the fuel handling and auxiliary building. And, that meant there was obviously high activity in that building. And the operator said to me, got to hang up now, and hung up the phone. I said to myself, gee, this must be the biggie. And unfortunately, when the folks from Washington came to debrief us and do depositions, I made the mistake of saying that my thought was, this is the biggie. Well, it became the title of a chapter in the first NRC report that came out. This is the biggie. So that's a hell of a way to get your names and thoughts in light. Later that morning, I was called. We established an open line with the control room, and we could ask them any questions that we wanted, or they would tell us things that were happening at the plant. I believe that the plant operators were being very honest. They were not trying to hide anything from us. So I think, as you'll later see, the real problem was communicating things to the public and the public's understanding of what was really going on. Later that morning, we got a call from the Lieutenant Governor's office to have someone come over and give him a briefing on what was going on at the plant. Well, obviously, I got that unenviable task, and I talked to the plant and said, put somebody on, that really knows what the status is. So I talked to the plant manager, And he, among other things, told me that they thought they had primary to secondary leakage, and that the block valve, or the pressurizer power operator relief valve had stuck open, but they had closed the block valve. There was probably some clad failure, or fuel failure, but they didn't think it was appreciable. Uh, and that they had isolated steam generator because of concern about primary to secondary leakage. Well, the reason for the briefing was that the lieutenant governor, who is also the head of the emergency management agency, was going to be giving a press conference later that morning. So I went over, briefed the lieutenant governor. At the time, obviously, one of the questions was, are there any releases occurring? At that point, there were not, where there were no detectable radiation levels off-site. So after we prepared a short statement, basically saying that, there had been an incident, but there are no releases from the plant. Well, on the way over to the press conference, I called our office, and we started seeing low levels around the plant, and our teams that were sent out were seeing some radiation levels off-site. Again, primarily noble gases, or almost entirely noble gases. We were about an hour late to the press conference, so you can imagine the press there were quite anxious, and the lieutenant governor got up and made the statement, and then said, "We'll take questions." And of course, the press started asking technical questions. Well, somebody grabbed me and pulled me to the microphone, and here's a picture of the lieutenant governor and me during that press conference. Notice that late 70s hairstyle. It was in vogue back then. But the press started asking me questions, and right away I knew we were in trouble, because I would use technical words like reactor building, millirem, and of course the response was, "What is that?" And I think it's important to notice that the press really didn't take any initiative to gain more knowledge of nuclear power terms and things in general. In fact, Penn State offered a course for the press, and nobody showed up. After that, I went back to the plant. Obviously, some folks from the NRC region arrived at the plant. There was no NRC inspector assigned to the plant at that time, and we kept an open line with the plant and continued to have dialogue with them based on what was happening. I think really, I guess the only thing that really happened that day of note was that at about 6 p.m. they were able to get the core covered and remove the voids in the system, and they were able to start a main coolant pump. At that point, basically the plant was in a stable condition, and things should have gradually gotten better and improved from that point on. I came into work on Thursday and decided that I would go down to the plant observation center, which was right across the river from the plant. Uh, Obviously, there was a lot of press there, uh, and the Med Ed officials were doing press conferences, and unfortunately, the VP of nuclear in his press conference he was very arrogant to the press, and the press was asking questions, and the manager said at one point, well, maybe if you'd stop asking questions, we could get to work on getting total control of the plant. Obviously, that didn't go over very well, and the media lost a lot of confidence in Med Ed in terms of their credibility. Also on Thursday, while at the plant, and we'll go back to this, because obviously they didn't want this makeup tank to lose liquid volume, there's a vent on the tank, and they were periodically venting the tank to the auxiliary building to maintain an adequate level in that tank. They would notify us before they did that release, and a state police helicopter would fly above the vent and take radiation levels. And I vividly remember seeing radiation levels at this point as high as 3,000 millirem per hour at, very near the plant vent. And, off-site, probably the levels were in the hundreds upriver of the plant. Luckily, during the early phases, the plume was blowing upriver and was really avoiding a lot of populated areas. So I was not real concerned, when things on Black Friday, which is what we call Friday, when NRC mistakenly misinterpreted a reading, a radiation level from the plant. Again, on Friday when I got to work, I mean, things were still improving. The plant was actually the plant at that point was in a low pressure cooling mode. So it was in fact very stable. Releases were still occurring because of the need to vent the makeup tank. At about 10 a.m. on Friday, we heard the siren sounding. So what the hell is that? And so we tried calling PEMA, the Pennsylvania Emergency Management Agency, but because of the concern, we didn't have any dedicated lines at that point. We couldn't get through because of the increase in calls. So my boss went over to the governor's office, and I went over to the PEMA headquarters, which was in reasonable walking distance, saying, hey, what's going on? We have no idea what's happening. Well, apparently what happened was the NRC, there was a release ongoing, and the radiation level at the vent was 1,200 millirem per hour. Now, obviously, that was a lot less than the previous day. So it meant that obviously the releases were decreasing. But either the NRC had manned their incident response center down in Washington, and either the the resident inspector or the regional inspector or somebody at the incident response center misinterpreted that reading. They thought it was an off-site reading, 1,200 millirems off-site. So obviously that raised a lot of concern, and they decided they would call PEMA and recommend an evacuation. We immediately called the incident response center livid. You know, what the hell are you all doing to us? We're the ones that are supposed to make emergency protection recommendations, and we haven't seen anything that would cause that. Well, in response to that, the alarm went off. It was decided that there would be a take cover order issued, and that also occurred later. And I was actually in the governor's office when this occurred. The governor was talking with the chairman of the NRC, and the NRC chairman kind of just without said, well, if I had a pregnant woman or child in the area, I would probably want to get them out of there, because they were still concerned about other things, that were occurring at the plant. Primarily on late Thursday, remember I mentioned the hydrogen that was being generated? There was a 28 PSI pressure spike in the containment that at the time nobody really noticed, but later on the strip recorder, they noticed it, and because of nothing was really damaged in the containment, it was probably a very quick hydrogen burn. Obviously, that caused concern because they knew there was hydrogen in the containment, and obviously, if the hydrogen level gets to a certain point, there could in fact be an explosion. They were calculating doses that were unbelievable. If there was a hydrogen explosion in the containment and it was breached. So the governor implemented the pregnant women and children evacuation out to 5 miles. One of the problems, though, because there was really nothing of significance to cause that recommendation, it was very difficult a week or two later to find something where we could say this evacuation is no longer needed. We can bring people back. So it was kind of ironic that we did an evacuation for no reason and had no reason to end it. One of the things that also occurred over the weekend that was probably even more traumatic to the public, and that's the hydrogen bubble issue. And we'll go back to this. There was a void in the top of the reactor vessel that was obviously full of hydrogen. The reactor coolant system was saturated with hydrogen. And when I heard about this from my Navy nuclear experience, I knew that we deliberately injected hydrogen into the system to prevent radiolysis from occurring. Now, radiolysis is a breakup of water into hydrogen and oxygen by radiation. So no oxygen could have been generated in this bubble, and therefore, without oxygen, there was no concern about a hydrogen explosion in the vessel. Unfortunately, there was some differences of opinion within the NRC, and also on Friday when the NRC folks arrived in mass, I was sent down by the governor to be in the trailer with Harold Denton and the other NRC managers and kind of act as a spy and report back directly to the governor. Well, like I said, there was a bit of difference of opinion. Harold Denton was primarily the spokesman, and he wasn't very much involved in this decision. But one of the managers, Vic Stello, he agreed with me that it was not an issue. Unfortunately, there was another manager that did not agree, and he had some national laboratory people working on the problem, but they were using the wrong assumptions. They assumed that this was occurring, this hydrogen bubble was at atmospheric pressure. Obviously, that was not the case. So at atmospheric pressure, obviously, there could be some oxygen being generated. So the whole premise that this was an issue was false. And that came to a head on Sunday when President Carter visited the site. Obviously, we didn't want the president there if there was any concern about a hydrogen explosion. Now, when you talk about explosions at a nuclear power plant, obviously, first thing that comes to mind is a nuclear explosion. And obviously, that is not capable with a light water reactor. But the public obviously became very concerned, and that's when most of the voluntary evacuation occurred, when they heard about this hydrogen bubble. Finally, the NRC was convinced that this was not an issue, and the bubble kept decreasing because the hydrogen was being dissolved in the coolant. It was being released to the makeup tank. Unfortunately, the NRC didn't tell anybody that this was not an issue. They kept the myth alive, and they didn't say it was all over until Tuesday, when there was no more bubble in the top of the reactor vessel. They were more concerned with their integrity than they were with the truth at that point. In fact, on Saturday evening, I was asked to go brief the state legislature up at the governor's mansion, and I figured, hey, I'm going to be honest, and I told them that to me there was never any concern about the hydrogen bubble. Well, obviously, I wasn't supposed to say that, because they very quickly ended my presentation and got me off the stage. So, sometimes it is a problem when you tell the truth. Again, the hydrogen bubble went away, and it was reported to the press and the public that it was no longer a concern. I think it's important to note that on Thursday, like I mentioned, on Thursday evening, the accident, the immediate concern about the plant's status was really over when they restarted the reactor coolant pump. And nobody was really aware of the amount of core damage that had occurred. There was concern that there probably was core damage, more in the nature of clad failure, and mainly, and I thought this too, because when like the reactor coolant pump was restarted, the system behaved as you would expect it would. Not as if there was a large amount of core damage. there was a lot of obvious monitoring going on by both the med ed folks, us, and other groups that came in, including DOE and EPA. Based on the measurements, it was estimated that about 14 million curies of noble gases were released. And luckily, only 14 curies of iodine were released. The maximum milk is a very good indicator. Cow's milk is a very good indicator of iodine release. And we saw levels in milk of no more than 20 to 30 picocuries per liter, which is well below, any level of concern. However, we have the Hershey foods in Hershey. Obviously, they use a lot of milk, and there was a lot of concern about milk. However, I vividly remember about a year previously when the Chinese were doing above ground testing of nuclear weapons. We saw levels of iodine in milk that were about at least 10 times that level that we saw from the TMI accident. And, at the time, no protective actions were required or taken. You can see this is an example of some of the news headlines that were occurring. The further away from the plant you got, the more disturbing the news was. In fact, I saw newspaper reports that said thousands had died in the Harrisburg area from the TMI accident. The local media and the local radio, I think, did a pretty good job in terms of putting out factual information based on what they had. I think maybe because they were more affected by what was going on, but they did a pretty good job. One of the biggest issues was communications. In the beginning, everybody was trying to communicate with the press, the state, med ed, and the NRC, and there was conflicting information being given out. That changed when the NRC arrived and Harold Denton became the only spokesman for what was going on at the plant. For those of you that know Harold, he had a very calming voice, a nice southern drawl, and he did an extremely good job in terms of communicating with the media. However, and he admit this till his dying days, that it took a while, but he finally admitted that he was the one that made the decision to recommend an evacuation. Just to give you some perspective on the TMI dose compared with natural background, the total natural background in Harrisburg is roughly about 116 millirem per year. Living in Denver, because of altitude, adds another 30. Being in a brick house compared to wood, another 14. The variation in natural background radiation, and all of these are without radon, of course. They're just terrestrial and cosmic radiation. There could be a variation of 100 to 130 millirem per year variation within 50 miles of TMI. The highest estimated dose of anybody remaining out of doors for the entire duration, which for this report was 11 days, would have received less than 10 millirem. I think it was it was actually calculated to be 85 millirem. The average dose within 50 miles of the site was about 1.5 millirem, and within 10 miles, 8 millirem. The total population dose within 50 miles was 3,300 person rem, and natural background radiation during this same period would have given 3.5 millirem. So you can see, the dose from TMI was well within the the uncertainty in or the variation in natural background radiation, and was about within 10 miles was about let's say 3 weeks worth of natural background radiation. Population dose within 50 miles was 7,500 person rem. I think it's also important that all this dose to the population was noble gases. And noble gases are unique in that they do not, because of their noble gases, they do not interact with organs, give specific organ doses. The only effect they have is gamma and X-rays that come from the cloud as it passes over the population. So, it was obviously less than a typical X-ray in terms of exposure to the public. This is an estimate of the dose distribution. This is 10 miles. This is 20 miles. 10 millirem, 50 millirem, 1 millirem. You can see that, like I said, the primary dose was on an axis with the river. And the highest dose, I don't know if you can see it, was on an island in the middle of the river, which has some homes on, but at that time of year they weren't occupied, so that was really not a concern. This is a chart of the individual dose and also the population dose. And as you can see, on Friday, the 30th, Black Friday, the peak dose had almost been reached. So, the evacuation really at that point was not very effective, and it continued slightly, but it very much leveled off. This is some pictures of when they finally well, one of the concerns was the krypton that was in the reactor building. So we had to devise a method to release the krypton, and believe it or not, somebody got the bright idea of asking the public for ideas of how to do that. Well, you couldn't imagine some of the ideas that were submitted. But anyway, it was decided that it would be released gradually. The reactor building could then be occupied. I actually entered the reactor building right before they closed it. Obviously, I had to dress up, in protective gear, and I think I received I was in there for maybe half an hour, and I received about a 20 millirem dose while I was in there. But these are pictures of the insertion of cameras into the core, and this is a picture of the core, and I was quite shocked when I saw these pictures. the core damage. Here is a schematic of the core damage. You can see that significant, probably about 2/3 of the core was melted. There was debris, a crust. There was you know, liquid that probably you know settled on the floor. Nothing other than this. The real damage that occurred to the core fortified my faith in light water reactors. I never thought that you could do this much core damage and not have a melt through and a containment breach and just an incredibly terrible accident consequences. So, amazingly, with this much core damage, the impacts were relatively minimal. I think the main issue, we scared the hell out of about 1 million people due to poor coordination of decision making and communication. There were obviously, with that dose, there were no calculated impacts, radiation impacts from the accident, but I think there were a lot of mental health impacts that are very difficult to quantify. There were numerous studies that were done that confirm that in fact there should have been no health effects from the accident. The lessons learned greatly improved light water reactor safety. I think that was one of the primary benefits of the TMI accident. Before that, there was an accident waiting to happen. When I was visiting the other plants as the state's nuclear engineer, there was a lot of false confidence in the operators that nothing could ever happen, and it was a very big concern. So this obviously changed that attitude and made reactor safety a lot better. And obviously, since then, we've never had anything near any incident that really released a lot of radiation. One of the biggest untold stories is how the nuclear industry responded to the accident to assist in response efforts. Also, a lot of organizations that hadn't been in place before, industry organizations, were formed, and that greatly improved the safety of the plants. Procedures were revised. A lot of areas were improved. Obviously, it was a big factor in no new plant orders, and then when plant orders started, the Fukushima accident put a kibosh on that. I'm not going to read these, but this is a list of lessons learned that was done by my colleague Maggie Riley. Maggie and I obviously were key responders. She was primarily on the radiation side. I was on the nuclear safety side. But Maggie had a kind of a weird sense of humor. So you can see some of these are kind of humorous, but they are in fact very true. I assume you will be getting a copy of this presentation, and you can read these at your leisure. But let me pick one out here that Yeah, here's a good one. Protective action recommendations are not amenable to committee vote, meaning the NRC. And here's another one right below it. When something big happens, there are many who think this is a chance of a lifetime. I may never again have the opportunity to affect the outcome. How can I screw it up? It is, they won't, and they do it in many ways. Here's repeating what I said. The national media people in general are an unmitigated pain in the butt. Local radio guys are great. And this is really obviously important. Keep a sense of humor. Uh, I don't know how we would have survived without this in mind. You have to keep a sense of humor and try to keep things light. Or, if you take it too seriously, you're going to affect your own mental state. I think that's all I had. With that, I'll be glad to answer any questions you have.
Bill, that was just fascinating. Yeah, this is Scott. I got a couple of questions. Since TMI and throughout my career, we've both worked for the NRC for many years. At the time of TMI, the NRC was, it had only existed for just a few years. And I know I've seen the industry as well as the regulatory staff and bodies mature considerably, embrace lessons learned. We at Savannah River have taken the events that took place at TMI, and we talk about that frequently as part of our nuclear safety culture. I think it's really important to gather these lessons learned and to learn from past mistakes. And I know that you were interviewed, I think, recently for quite some time. There's going to be a Netflix documentary released here in several months, maybe at the end of the year. I don't know if you can elaborate on that.
Yeah, sure. I'm probably one of the last surviving key participants in the TMI accident. So particularly on the TMI accident anniversary, I'm asked to do interviews and other things, and periodically make presentations. Netflix contacted me recently and interviewed me for 5 hours. They're doing a 4-part series on the TMI accident. And based on the questions they asked me during my interview, and also, assurances by the producers that it's going to be a fair presentation. And it was supposed to be out earlier this year, but obviously the pandemic and other things have delayed everything. So hopefully it'll be coming out hopefully by the end of the year. Yeah, I think Scott is right on in terms of lessons learned from the TMI accident. In fact, there was an NRC report put out that detailed in great depth what those lessons learned were. And like I said, it went a long way toward making light water reactors a lot safer. And obviously the new generation of light water reactors are, almost accident proof.
Well, the next thing I'd like to talk to you about was the memoriam that you wrote for Maggie Riley. Now, that was published as part of the Health Physics newsletter, and I thought it was just outstanding, and it captures each of these lessons learned as well. So what I've done is I've forwarded that to the folks that handle our internship lecture series, and that tribute to her, as well as those lessons learned, will be shared with our interns. because I thought you did an outstanding job in capturing she was a brilliant lady. Her career was very successful. She was very active in promoting women in sciences and engineering. So anyway, I thought that she would like that, but I also thought that you would. So we'll be sharing that as well as your presentation.
That's
And my
great.
last
Thank you very
question
much.
before I open it up is,
Well,
what
let me
do you
just
think is the
comment on
single
that.
most important piece of advice that you could give our interns that will ensure they have a successful and rewarding career?
Well, first I want to make a comment about Maggie. Maggie retired from the state I guess, about 3 years before I did. And obviously, she and I remained good friends. We had lunch together about once a month. And she, in fact, made me executor to her will. And she got even because she was a hoarder, and it was not easy cleaning up her estate. Uh, but another humorous story about Maggie. Initially, I worked for her, and eventually, when I became bureau director, she worked for me. So it was a kind of interesting switch. But first meeting we went to when I joined the bureau, we were eating lunch, and I spilled a glass of beer all over her. Obviously, I thought I was going to be beaten down. But and then it, for her retirement, I was the master of ceremonies, and I said, Maggie, all these years we worked together, there was something that I always wanted to say to you. Maggie, shut the hell up. And that Maggie was an incredible person. She will be greatly missed, and her legacy will live on. In terms of recommendations or suggestions about your future, I think don't be dismayed by the the things that are occurring in the nuclear industry at this point. I think obviously we need base load power. Coal is no longer an option, and I think that will die out. Uh, Natural gas prices will rise, and once again, nuclear will be the most commercially acceptable and cost wise source of baseload power. The solar energy, it's difficult to store, and if we're going to be having a lot of electric cars, we're going to need electricity, and I don't think the non baseload sources will provide that electricity. So don't get discouraged. I during my career, I changed primarily from being a nuclear safety person to a waste management person, and that was obviously a growing industry, and it still is. There's a lot of sites that need to be cleaned up, so there's always other options besides nuclear safety. But I think nuclear safety will eventually come back.
Bill, with that, we're going to turn this over to Leslie for some questions and answers from the audience. So, Leslie, you got it from here.
All right, so we don't talk over each other. If people could use the raise their hand function, and I can call you out. We had one question in the chat. Since about 14 curies of iodine 131 was released in the environment, was the population around the plant given potassium iodine as a conservative measure?
No, they were not. Mainly because the levels were so low. Nobody was given it for the Chinese nuclear test that I mentioned. I think I don't remember what the what the recommended levels are for giving out potassium iodide, but certainly wasn't anywhere near that. I think we were in the process of trying to find it just in case. So it was not something that we weren't aware about or, potentially considering. Oh, one more story about iodine that I think you'll find interesting. We were doing all kind of sampling, including the river, and we saw a very low level of iodine at the discharge of the TMI plant. Well, we also were doing radiation measurements at the intake, and it was basically the same level. So we decided, where is this coming from? So we went upriver and saw that there's a creek that goes by the Hershey Med Center, and in fact, that iodine was coming from folks that were getting iodine treatments for thyroid and being sent home, with still some iodine load in their body. In fact, the plant was cleaning up the river because of the decay time for the water to go through the system. At the discharge out in the river, there were levels. At the discharge itself, the levels were 0.
Okay, Bill, we're going to conclude the presentation, but this was outstanding. Thank you so much on behalf of our interns that are here for this summer. Again, that was just fascinating. So we'll conclude this, but next Wednesday we'll have another presentation, but it'll be on the Fukushima accident and the National Academy of Sciences reports. And that will be presented by Miss Barbara Hamrick. And Barbara is, I think you guys will find her outstanding. She's a former state regulator, just like Bill. She was on the National Academy's committee that studied the Fukushima event. She's a certified health physicist and as well as an attorney. So join us next Wednesday at noon. And Bill, thanks again.
Scott, just one more thing. About 2 months after the accident, I wrote a paper and presented it numerous times that kind of details, the state's response, what caused the accident in detail, and a lot of the things that I presented, to you today. If you're interested, I can certainly provide that paper to Scott, and he can make it available to you.
Most certainly, please do, and I'll share that, Bill.
Okay.
Okay, with that, our presentation concludes. So thank you guys very much. And Bill, thanks a million.
My pleasure.